Welcome to the weekly Greenwich RMA speaker program. We have another exciting talk this morning, one that is literally out of this world. First, a couple of reminders. To ask a question, go to the Q&A at the bottom of the screen and type your question. I will convey them to our speaker after his presentation. For more information on the RMA and for a selection of hundreds of recorded previous talks, go to greenwichrma.org. Next week's speaker will be John Seelock, an award-winning political writer who has influenced legislation in many states. He will talk on how young elected officials are impacting the United States, a timely topic indeed. And now it's my pleasure to introduce Bill Diamond, the CEO of the SETI Institute in Mountain View, California. The SETI Institute is a nonprofit astrophysics and astrobiology research and education organization. Mr. Diamond has held various executive management positions in applied technology. He has over 30 years industrial experience with startups and Fortune 100 companies in laser photonics, optical communications networks, X-ray imaging, and semiconductor processing technologies. He holds a BA in physics from Holy Cross College and an MBA from Georgetown University. He's a past member of the advisory board for the McDonough School of Business Administration at Georgetown, and he also serves on the board of directors of the Bay Area Science and Innovation Council in San Francisco. So welcome, Bill, and please take over.
Well, good morning, Arnold, and thank you very much. Let's get started. So good morning, ladies and gentlemen, and thank you for coming on today's journey with me. It begins somewhere on this small rocky planet that we call home, a few 100,000 years ago, when one of our early ancestors gazed up at a star-filled sky with wonder and curiosity. Curiosity, perhaps that most unique of human traits that unites us all and distinguishes us from all other species on the planet. It's the essential ingredient of all scientific inquiry, including the search for life beyond Earth. Today, I invite you to join me on a quest, on a journey of ultimate discovery, a journey that begins and ends with our curiosity. I'm Bill Diamond. I'm the president and CEO of the SETI Institute, and it's my distinct honor to be today's guest speaker for the Retired Men's Club of Greenwich. And how much of an honor it is, let me just say that I haven't had a white button-down shirt on for about a year now. So indeed, it's a great honor. This morning, I'm going to discuss the search for life beyond our own planet and start with some information to help scope out the scale of the challenge. I'll then introduce the Institute and talk about the roadmap that guides our endeavor. Next, I'll briefly describe the methods and approaches we apply to our research and provide some insights into what we have learned so far and what we still have yet to learn. I'll wrap up with a review of education and outreach programs at the Institute that leverage everyone's fascination with space and the unknown, and finally, offer some closing thoughts for your consideration. So let's get started with some high-level perspectives to provide a bit of context and background to the nature of our work. Humanity is on a quest, and it's a quest that began thousands of years ago when our ancestors first gazed upon the starry sky and wondered, are we alone? We still want to know, is our world unique in harboring life among the billions of similar worlds in our own galaxy, or has life sprung up elsewhere and had the chance to evolve to the development of complex organisms, perhaps including intelligent creatures, or even advanced technological civilizations? It isn't a new question. Indeed, it's a question that's captured the imagination of many, from Galileo to Einstein, Winston Churchill to Nancy Grace Roman, Cornell's Carl Sagan to Harvard's Avi Loeb, and SETI Institute co-founder and Carl Sagan protege, Jill Tarter. Jill is a SETI pioneer and also the inspiration for the Ellie Arroway character played by Jodie Foster in the movie Contact. Actually, NASA also wants to know. In fact, there are three basic science questions that guide the US Space Agency. The first is, how does the universe work? The second is, how did we get here? And the third is, are we alone? Indeed, even the Pope wants to know, along with this gentleman, Brother Guy Consolmagno. Brother Guy is a member of the Science Advisory Board to the SETI Institute and also happens to be the astronomer to the Vatican. I think it's fair to say that when it comes to the question of life beyond Earth, we all want to know. I think we're all curious about this question. But what sets us apart from those who've wondered before and what makes this particular moment in history so important is that actually for the first time, we have the tools and the technology to find out. We have the ability to answer that question. So before we plow ahead, however, with all of our technology and begin our search, it's important to try and understand just the scale and the sheer magnitude of the quest. After all, the universe is a pretty big place. Our solar system is an insignificant collection of planets around a very ordinary star at the edge of quite an ordinary galaxy, and yet even here, the scales are impressive. In our own backyard, in just our solar system, we have 8 planets. We have 5 minor planets, more than 200 moons. There are 3,662 known comets, and certainly many more we have yet to discover. And there's surely more than 1 million asteroids whirling around our sun. To give you some idea of the size, if you were a photon of energy traveling from the sun to Pluto at the speed of light, it would take you 5.5 hours just to get there. And if you were to send a spacecraft to Pluto, as we did back in 2006 with the New Horizons mission, it would take 9 years to travel that same distance. 9 years on a spacecraft just traveling within our solar system. Our home galaxy is the Milky Way. I think you've all heard of it. And perhaps some of you, lucky enough, on a starry, clear night have been able to see it as well. But its size is extremely difficult to comprehend. It's over 100,000 light years across. That means that traveling at the speed of light, it would take 100,000 years just to get from one side to the other. There are approximately 300 billion stars in the Milky Way, and our nearest neighbor, Alpha Centauri, is just a mere 4.2 light years away. And yet, if you sent the same spacecraft that visited Pluto to our nearest neighbor at its current speed, it would take 17,000 years just to get there. So as neighbors go, Alpha Centauri is very distant in every sense of the word. And yet the Milky Way galaxy is just one of hundreds of billions of others. Each little smudge that you see in this image, which was taken by the Hubble Space Telescope, and it's called the Hubble Deep Field, is a galaxy, not a star, but a galaxy. Each one contains hundreds of billions of stars, and thus hundreds of billions of worlds. And we'll talk more about that later. The scale is truly unimaginable, but hopefully this gives you a sense of what we call the parameter space, or the volume of space that our quest embraces. So what's our place in this cosmos, and where do we fit in? Well, that's where we come in, so let's meet the SETI Institute. Our vision at the SETI Institute is to inform and educate and inspire through exploration and discovery to understand our place in the cosmos and unite humanity by exercising our common curiosity. And our mission is to lead humanity's quest to understand the origins and prevalence of life and intelligence in the universe and share our work with the world. The SETI Institute is organized around 3 core activities or business centers. We have the Carl Sagan Center for Research for Exploration. We have the Center for Education to inspire, and the Center for Outreach to engage the public. The SETI Institute is home to more than 100 PhD scientists, plus 34 education, communication, and professional administrative staff. We're a 501c3 nonprofit research institute. We're funded by federal research grants and contracts, private foundations, corporate partners, and private individuals like you who care about our work. We are a top 100 NASA contractor, and we collaborate with academic and research institute partners around the world. And fundamentally, we're passionate explorers, we're pioneers, we stand on the shoulders of giants in pursuit of new knowledge and understanding that's built on a foundation of rigorous science. But given the magnitude of the question and the sheer scale of the cosmos, where do we even begin? How do you start such an endeavor? Well, let's start with the following. What if someone asked you to calculate or estimate the number of technological civilizations there might be in our galaxy? And what if that someone was NASA? Well, that's precisely what happened back in 1961 when NASA asked Frank Drake, Carl Sagan, and 10 others, who later became known as the Order of the Dolphin, to review this question. The group gathered for a meeting at Green Bank, West Virginia, at the then new National Radio Astronomy Observatory to discuss the matter. And it was Frank's job to put together an agenda. So Frank thought, we need to know some basic things about the universe around us. We have 7 questions we should answer if we're going to try to estimate the likelihood and indeed the number of potential technological civilizations that might also exist in our galaxy. We need to know things like the birth rate of stars and how many of those stars have planets. How many planets among those are habitable, Earth-like planets in that so-called habitable zone or Goldilocks zone where the temperature is just right based on the distance to the star for liquid water to be maintained. How many habitable planets that would then go on to develop life? And of those, how many develop intelligent life? And if intelligence emerges, how often does technology arise? Does it have enough time to take hold? And when it does, how long might a technological civilization remain detectable? So he soon realized that his agenda and list of questions could be organized into a bit of a formula, or in fact, to a method to calculate the number of technological civilizations that might exist beyond Earth as a kind of probabilistic model. His formula soon became known as the Drake equation, which you see here, and is considered by many to be the second most famous equation in all of science. And of course, I hope I don't have to tell any of you what the most famous is. What Frank did not quite realize at the time, however, was that his agenda and this formula essentially established a roadmap for the field of astrobiology, or the study of life in the universe. To look for life beyond Earth, we need to know about stars and their life cycle. We need to know how many have planets, how many habitable worlds there might be, how many go on to develop life, intelligence, technology, and then how long they last, or how long they at least remain detectable. It looks a bit complicated, but it's really quite simple. And you can think of it like a funnel. And at the narrow end of the funnel, out pops an answer of how many technological civilizations there might be. Maybe many, or maybe one. Frank is still very present and right now retired. He's an emeritus trustee at the SETI Institute. And of course, he serves as an inspiration to all of us. So let me pause here a minute, and I'm going to ask you to look at this photograph. And actually, while I do that, I'll have a sip of water. And I want you to stare at all the stars in this night sky. And I want you to open your minds up to an incredible possibility. What if every single one of the points of light in this picture was a star with planets, a star with its very own solar system? I'm wondering if you'd find that hard to believe, or if you could even imagine this to be the case. So let me let you in on a little secret. They all are. All of them, every single one, statistically is another solar system, a star with planetary system around it. This is no longer a matter of speculation, and it's not science fiction, it's science fact. But how do we know that? We know because of the discovery of so-called exoplanets, or planets orbiting other stars, other suns. In 2009, NASA launched the Kepler Space Telescope, which was purpose-built to determine if newly discovered phenomena of planets orbiting distant stars, so-called exoplanets, were an astronomical anomaly or indeed something quite common. Kepler used the so-called transit method, detecting the presence of orbiting planets by observing the very slight dimming of the starlight each time the planet would pass in front of the host star. The result of its 9-year mission were profound in the extreme and forever changed our perspective on humanity's place in the cosmos. The SETI Institute not only managed the data pipeline for the Kepler mission, but our software engineers wrote the algorithms for the planet detection. What did the Kepler mission discover? Well, the first exoplanets were discovered in the early 1990s, but it wasn't even until 1995 that we understood the phenomena being observed were actually other planets. Prior to the Kepler mission, most exoplanet discoveries were made by the so-called radial velocity method, where the presence of a large planet orbiting a star resulted in the apparent wobble of the star caused by the moving center of gravity between the star and the planet. And of course, very big, heavy planets would have this impact on a star that we could visualize here on Earth. Not many Earth-sized planets were detected through this method. And you can see on this plot here a scale where on the vertical axis, you have the planet's mass, where Earth is mass 1. It's that line near the bottom of the chart. But thanks to this transit method and extremely sensitive instruments on the Kepler mission, thousands more planets were discovered, with the vast majority being between Mars and Neptune in size, implying that billions of Earth-like planets exist on our own galaxy. So all those yellow dots that you see are planets discovered by the Kepler mission. And you can see on the plot how so many of them are centered in size or mass around the size between Earth and Neptune, or actually Mars and Neptune. So billions of Earth-like planets. So what did we learn? Well, we learned that planets are everywhere. They are ubiquitous in the known universe, and they likely outnumber the stars. NASA's mission, the Kepler mission, taught us that every star in the sky has one or more planets. The majority of planets fall between Mars and Neptune in size, like Earth. Approximately 20% of all planets are rocky, Earth-like habitable zone worlds. And that means potentially 10 to 60 billion Earth-like habitable zone planets, and that's just in our galaxy, the Milky Way galaxy alone. So let's take a look again at the Drake equation, 60 years after that fateful meeting in West Virginia, since the very first SETI experiments were conducted there by Frank Drake himself. What have we learned since that time? Well, we know the birth rate of stars, which we've actually known for decades. It was probably the only variable actually known at the time of the meeting, at the time that Drake equation was concocted by Frank. We also know that planets are everywhere, and we now also understand that habitable worlds may be as much as 20% of all worlds. And yet there's still a lot that we don't know, such as the origins of life and the conditions under which it begins. We don't know much about the evolution of intelligence from the onset of life, nor do we have any examples but ourselves of technological civilizations. And of course, we don't know how long civilizations like ours remain detectable before they go dark for whatever reason. So the unknowns mean that there's plenty more work to be done, but somewhat paradoxically, the more we learn, the more new questions we raise. So let's talk now about the methods and approaches we undertake to answer them. So we have a structured approach to address what is essentially a singular science question. Are we alone in the universe? So we address this question within three fundamental domains of research: the structure of the universe, planets and habitability, life, complexity, and intelligence. These domains are then investigated through 6 individual branches of research at the Institute. They include astronomy and astrophysics, exoplanets, planetary exploration, climate and geoscience, astrobiology, and finally, radio and optical SETI, or the search for technosignatures as a proxy for life and intelligence. Our scientists come from 23 unique and distinct academic backgrounds and research backgrounds that cover pretty much the full spectrum of the natural sciences. And our work includes NASA science mission support. We do field expeditions, laboratory research. We make ground-based observations in both the radio and the optical domain. We use space-based observations from instruments like Hubble, Kepler, TESS, New Horizons, Cassini, and others. And we do technology and instrumentation development, including, for example, on the Curiosity rover, the precursor to the Perseverance rover now on Mars. There's an instrument called the ChemMin system, which is an X-ray diffraction instrument designed to understand the material composition of Mars. And that was designed and developed by a scientist at the SETI Institute and his colleague at the NASA Ames Research Center. We endeavor to understand through our work the structure of the universe, planetary environments, and the notion of habitability, what that means, the nature and origins of life, and the evolution of intelligence and technology. So a typical day at the office includes science support for NASA missions like Cassini or TESS or Curiosity or New Horizons and more, including now the Perseverance rover and Mars 2020 mission. Institute scientists have been involved in pretty much every unmanned NASA mission since Voyager. We also use ground-based observatories such as our own Allen Telescope Array, the Very Large Array in New Mexico to search for signatures of technology among the stars. We undertake field expeditions around the world, including Devon Island in the Canadian High Arctic, Lake Untersee in Antarctica, and research in the Atacama Desert, the Andes and Altiplano of Chile and Peru, and beyond. So combined with laboratory research and advanced data analytics and applied machine learning, our science pretty much covers all the bases. But what makes us different from other research or academic institutions? Well, this is an interesting question, one that we think sets us apart a little bit from other organizations. You know, humanity's approach to understanding nature is deconstructionist by design. We tend to break things down into component parts we can digest and comprehend, and we organize our knowledge into disciplines like chemistry, physics, biology, astronomy, and geology. At the SETI Institute, we employ a multidisciplinary approach and work to put these knowledge foundations back together to form a more holistic understanding of the natural world. So we explore the interdependence and the interconnectedness of all natural phenomena, understanding that real insight often happens at the intersection of disciplines and not necessarily only within the disciplines themselves. We call it connecting the dots. But what else sets us apart? After all, one of NASA's 3 science objectives is to answer the question, are we alone in the universe? So what's different about the SETI Institute? Well, it turns out there are 3 basic ways to look for life beyond Earth. First, there's what we call in situ analysis. This is a technique that involves sending analytical instruments, equipment, probes, landers, etc., to look for past or present life. The Perseverance rover is precisely such a mission, and it's the first NASA project specifically designed to look for signs of life on another planet. The second is remote sensing, where telescopes like the James Webb, which will be launching later this year, we hope, fingers crossed, will allow us to probe the atmosphere of distant planets to look for biosignatures or signs of possible life based on the molecular fingerprint life can leave behind in planetary atmospheres. And the third, of course, is SETI research, where radio and optical telescopes look for evidence of technology from distant worlds as a proxy for life and intelligence. But let's briefly look at each of these one at a time and understand sort of their parameter space, or the volume of space that can be investigated by these techniques. For all practical purposes, in situ techniques are limited to the study of bodies within our own solar system. From Venus and Mars to Titan, Europa, and Enceladus, there are perhaps 5 other candidate worlds besides Earth where life may have existed at one point in time or may still be present. Including the Oort cloud at the very edge of our solar system extends to no more than about 1.5 light years across. And we haven't yet developed the technology to send instrumentations beyond our solar system to look for signs of life. Billions of dollars are spent by the US and foreign governments to carry out this research, and that's entirely worthwhile. But our solar system is a mere microscopic piece of dust against the scale of the known universe. Remote sensing technologies like James Webb will push our research envelope or parameter space out quite a bit further as we explore the atmospheres and other characteristics of nearby planetary systems. At the scale shown here in this chart, our solar system is no longer even visible. But even out as far as 10 light years, our neighbors are still relatively few in number, with only a handful of possible worlds we'll be able to examine for signs of life. Perhaps another half a dozen or so candidate worlds. If we extend even further to 30 light years, which is about the limit of James Webb's capabilities in terms of probing planetary atmospheres, we see that the neighborhood gets a bit more crowded, but still the number of planets we can explore with remote sensing technologies will be quite small, perhaps only another dozen or so candidates. The James Webb Telescope is a $10 billion undertaking, and while exorbitantly expensive, there can be little doubt that it will profoundly expand and enhance our understanding of the cosmos, just as Hubble has done. And it will certainly profoundly change our understanding of our place in the universe. And the search for biosignatures in planetary atmospheres will, of course, be one of its many, but only one of many of its science mission possibilities. Yet with all this technology and its extraordinary complexity and expense, how far will we have looked for life beyond Earth? Frankly, not very far. Remember the Milky Way galaxy. Our solar system is located on a spiral arm towards the edge and is invisibly small on the scale of this image. In fact, if we were to consider the explorable space of 30 light years that James Webb will examine, it would be much, much smaller than the little red circle you see here. But SETI searches using radio telescopes can extend that exploration to the entire Milky Way, all 100,000 light years of it, and perhaps beyond. And the number of candidate worlds is tens of billions. And yet federal spending on this research is precisely zero. This seems ironic when one of our space agency's top science questions is, are we alone? It's like exploring planet Earth and trying to understand everything about planet Earth while standing still in one spot, turning your head around, looking from side to side, and trying to answer all the questions about Earth. In fact, the analogy is much more extreme than that. So if we conduct our SETI programs with private funding and collaborative research, this gives us the possibility to extend the search beyond the parameter space of the James Webb Telescope. This is what we do at the SETI Institute. Our three main programs for SETI observations at the Institute are the 6-meter 42-dish Allen Telescope Array, which is in Hat Creek in Northern California. We also use now, in a very new program, the 25-meter 27-dish Very Large Array, or VLA, in New Mexico, where we are launching a so-called commensal, which means simultaneous observation program in partnership with the National Radio Astronomy Observatory on what is the world's most productive radio telescope array. Each of those dishes, in fact, is a 10-story building arrayed over many, many miles in the New Mexico desert. And finally, our all-sky, all-the-time laser SETI program designed to look for laser pulses via a global observatory network. The first observatory is in Northern California, not too far from here. The second observatory will be deployed later this year in Hawaii, and with funding available, we will be expanding to a third observatory in Puerto Rico, and then begin development of 3 observatories in the Southern Hemisphere. So that's a bit of an overview about the research programs at the SETI Institute, and it hopefully provides you with some insights as to the nature of our work. I invite you to learn more at our website at SETI.org, and of course through our many outreach programs. But on that note, let me shift gears and address the second but equally important element of our mission, which is sharing our work with the world. Our education and outreach activities are all about leveraging the public's fascination with space exploration and discovery to design and deliver exciting and compelling programs. Sharing the knowledge we gain through our research, we think, is very important and is essential to our mission, as essential to our mission as the research itself. We believe that science literacy is essential to a thriving democracy and also a serious problem in our country, as I think we've observed in recent years and months. We feel a responsibility to do our part to address this problem, and we have what we think is a secret weapon at our disposal that we can deploy to make science literacy and science learning not only possible, but also fun. And that weapon is exploration. And not just any exploration, but space exploration. After all, what child isn't completely fascinated by space, its vastness, its mysteries, and of course, the profound questions it gives rise to. So what can we do to harness that fascination into an opportunity to learn through a context that is fundamentally and basically interesting and engaging? So at the SETI Institute, we have education programs that do just that. Our programs support teachers, undergraduates, and young children alike, and they include, among others, a program we call the Airborne Astronomy Ambassadors Program. This is a NASA-funded program for high school science teachers and now also middle school teachers, and we target underserved school districts across the United States. The program has been running for 10 years. We take selected teachers from these programs and we give them advanced training in astronomy and astrophysics, and in particular, infrared astronomy. We then give the teachers an opportunity to spend a week down in Palmdale in Southern California with the aircraft that you see here, which is a modified 747 operated by NASA and the German Space Agency, called SOFIA, the Stratospheric Observatory for Infrared Astronomy. And that opening in the back that you see is a 2.5-meter infrared telescope. And the aircraft flies above the atmosphere at about 45,000 feet to get above atmospheric water so that infrared observations can be made. So the teachers get a chance to spend time with the scientists, with the telescope operators, with the flight crew. They have, of course, an exciting and incredible experience. They get the very cool blue NASA jacket with patches and their name, and they go back to their school districts as local celebrities. They're also compelled to take part of their experience and embed it into their curriculum. And it's all about using this experience to inspire more interest in STEM topics and also better performance in STEM results. We also have a program called Reaching for the Stars, and this is a partnership with the Girl Scouts USA. It's another NASA-funded program. We also have partners at the University of Arizona and the Astronomy Society of the Pacific, among others. And what we've done is designed a series of 6 badges for the Girl Scouts, one for each of the 6 different age groups of the Scouts. And we endeavor to design material, activities, projects, and learning opportunities that the girls have to complete in order to earn their badges. Ultimately, it's about making a difference, and it's all about having impact. And in spite of our relatively small size as an organization, thanks to our partnerships and collaborations, our education programs have demonstrated significant reach and impact. For the teachers program, the Airborne Astronomy Ambassadors, we've had now over 200 alumni over the 9 years of the program. They've impacted more than 40,000 learners over that period of time. They've demonstrated student gains in standard-based learning and improved attitudes toward STEM subjects and careers, and these are independently verified as part of the NASA contract. We've had over 185 undergraduate interns over the last 15 years, and many of them have gone on to extraordinary fields in academia, in science journalism, and of course in other business and science ventures. We've had, in the very first year that the Girl Scouts program was launched, 65,000 of the youngest girls for the first 3 badges that came out completed that badge program in just 1 year. And in the second year, as we introduced the second set of badges, we reached over 100,000 young girls. So that to me is impact. That's something that I think we take great pride in at the Institute. And if we can impact the lives of 100,000 young girls a year and get them interested and excited about STEM and STEM careers, we think that's quite a difference. Also, we have new partnerships that are evolving with Cal Academy, the Chabot Space Science Center here in Oakland, California, and the Smithsonian Institute. So stay tuned and watch for further developments of our education programs. Outreach is also important, and engaging the public to both inform and inspire is equally mission critical to us. We take advantage of the public's fascination with all things space related, and we do this to reach out and touch lives. To see what I mean, look at these 8 images, and I want you to try and guess what they all have in common. And don't look at your astronomy textbook for the answer. What they all share in common is that these were all front page stories in the New York Times. So clearly, space science is newsworthy. The knowledge our curiosity has helped us gain is amazing, and space exploration is cool. It's exciting and it's fun. So why shouldn't we take advantage of those qualities to engage and enlighten the public, and of course, particularly children? We have a large number of outreach programs that include Big Picture Science. This is a weekly science radio program and podcast carried by NPR affiliate stations across the country. Our SETI Talks monthly lecture series, which has been running for more than 10 years now, has had hundreds of amazing lectures, panel discussions, and debates, all available on our YouTube channel. And of course, presently, we do them all virtually using Zoom. We have an artist in residence program at the Institute, where artists from all over the world work with our scientists for inspiration on amazing interpretations of their research: visual arts, performing arts, music, sculpture, and more, all of which are inspired by our science. And of course, we have a lively presence on all the main social media platforms. So let me close with some perspectives that might help put all of this into a broader context that is hopefully worthy of your consideration. All of our science and exploration, field expeditions, lab work, and data analytics are important. We think they're important, but some might ask, why bother? Don't we have more important problems to solve? And honestly, it's a fair question, but I answer the question as follows. Research and exploration exercise that most human of traits, our curiosity, and our curiosity is the engine for innovation. Without curiosity, there's no discovery, no insight, and no understanding. And I think it's fair to say that fundamental science and basic research are critically important as the precursor to all invention and technology development. You don't get tech until you do the basic science. Exploration stretches the limits of technology, which benefits everybody. And our work informs research in such areas as climate change, asteroid defense, communications and signal processing, cancer research, material science, sensor and instrumentation technology. Interestingly, Jill Tarter likes to describe our work as a little bit like holding a mirror up to ourselves, because as we explore life beyond our planet, we learn a lot more about life on our planet. So our quest is a journey of ultimate discovery. It's a journey to understand our place in the universe. It's a journey to leverage our curiosity for the advancement of human knowledge. It's a journey to be the archaeologists of our future and, in the process, to discover ourselves. And we'd like to think that the discovery of intelligent life beyond Earth will be among the most profound discoveries in all of human history. So are we alone? I say, let's find out together. I invite all of you to join us. If you'd like to learn more, you can visit our website at SETI.org. You can sign up for our monthly e-newsletter called Journey. You can join our Council of Advisors. You could talk to us about becoming a trustee. But now that you've enjoyed a taste of the appetizer, I do hope you'll come along for the main course. Learn more about us, join our quest, and become part of the SETI experience. So let me close by invoking the wisdom of someone who may be familiar to many of you, at least those of you of my generation. It was famously once said that the universe is a pretty big place. And if it's just us, it seems like an awful waste of space. And that was, of course, Carl Sagan. So with that, I thank you all for your kind attention, and I'm happy to take questions, and I'll stop sharing my screen to enable us to do that.
Well, Bill, tremendous. What a scope. As you probably know, one of the most burning questions by, I suspect, most people is, have you or do you believe that there have been any signals or other evidence of life anywhere in the universe? Maybe you would like to comment on the Oumuamua, if I pronounce that correctly, the fact they found phosphine in the atmosphere of Venus, for example, as possibly a signal of the presence of organic matter, and other reports that have seemed to indicate the presence or the possibility of life, especially if water was found, but that raises another issue. But first, you may want to address that question.
Sure. Well, it's a great question. I think it's fair to say, however, that if we had a definitive detection of life beyond Earth, and certainly any detection which would be indicative of a technological civilization or an intelligent species, I think it's fair to say you'd all already know it. This would be difficult news to keep under wraps, and of course it would be, among our most profound discoveries as a human species. So we don't have any hard evidence yet of intelligent and technological life on Earth. I hope, however, I've painted a picture where perhaps you might agree that the statistical odds are very much in favor for not just life, but even intelligent and technological life existing elsewhere. But we have no hard evidence. We do, of course, have some intriguing and teasing discoveries that have been made. And quite honestly, we know so much more about Mars now than we ever did before. We know Mars was at one point an ocean world. It looked very much like Earth. It would have been a blue planet, not a red planet, in its very early days. And there's flowing water on Mars. There's still water on Mars, locked in the polar ice caps, but also still flowing. And we can see evidence of water, for example, flowing down the sides of craters on Mars. And so that's why Mars becomes a fascinating candidate to look for past or present life, because while the surface of life of Mars is completely inhospitable to life, it could well be that a meter or so below the surface, you could still have microbial organisms that either have their origins tracing back to when it was a warm, wet world, or have evolved even since that time. Oumuamua was discovered by an observatory in Hawaii, which is why the Hawaiian name Oumuamua was given to it, and Oumuamua means the messenger. It's gotten a lot of news lately because Harvard astronomer Avi Loeb did some analysis, in fact, of the data of the trajectory and speed and orbital characteristics of that object as it came into our solar system from clearly interstellar space and then exited again. Comets, even though they come, in fact, very rarely into our visible spectrum, they orbit, and they are really members of the family of our solar system. So this was clearly unique in that it was an object that came from beyond our solar system. Avi's observations have suggested, to him at least, the possibility, because of some of the physics that he observed in things like the speed of the object as it left our solar system, that it was hard to explain those observational characteristics based on natural phenomena. And so he has speculated that, this could be an alien technology, an alien probe or visitor of some sort, or perhaps a so-called light sail that has come in to investigate our solar system. Of course, many people think that's a ridiculous statement or idea. But this is a gentleman with the credibility. He's was head of the astronomy and astrophysics department for many years. He's renowned for his work, and he bases his speculations on at least some sound science. So, and I think what's important about Javi's willingness to be controversial is that it brings the topic into conversation instead of a Oumuamua being buried in the back pages of the newspaper. And that's good. So in any case, there's no definitive agreement on whether that object may have been some evidence of alien technology, but it's intriguing. The phosphine in Venus's atmosphere is interesting because so far what we know about phosphine as a gas is there's no way to produce it without biology. It's a byproduct of biological processes. And so its presence on Venus, which is still itself somewhat controversial. It was a very, very, slight at the edge of instrument sensitivity observation. It's believed that the data is good, but certainly if it is proven to be phosphine, that raises intriguing questions. Of course, it is also possible that there are non-biological processes which, under the right circumstances, can produce phosphine. We don't know. But in any case, if that discovery is verified, raises some very, very interesting questions. Places like Enceladus and Europa, moons of Saturn and Jupiter, these could potentially house life. They're water worlds. They're covered in ice. Under that ice is a liquid water ocean. We know they're geothermally active, so they have heat and water and other building blocks. Very intriguing prospects for life. So no definitive discoveries yet, Arnold, but lots of intriguing possibilities.
Let's talk a little bit more about water. We have a few questions regarding water. For example, where did it come from? And do you really need water as the basis for life? Because I guess theoretically one could conjure up different systems that may be based, let's say, on ammonia, or even without a carbon backbone, because silicon is also capable of generating polymeric systems. Who knows whether they can generate what we would call life, however one wants to define it. So right. Can you comment on that?
Sure. So, this is a great question. First of all, water, H2O, is comprised of elements at the, small end of the periodic table. What people don't realize, and this, of course, is back to how science is taught and how we think that there's improvements that can be made. When you're taught the periodic table, you probably weren't taught that all the elements are born in the stars. So all the elements up to iron are born in so-called first generation stars. And the only way to generate enough energy to create atoms of greater structural complexity than iron is to have a supernova, to have this massive high energy event, an explosion that allows the bonding of smaller atoms into larger atoms in the periodic table. So that's something important to understand. So you've got water as a building block, which is among the most abundant of the elements. So actually another phenomena that's important to know is that the abundance of the elements goes pretty much in order of their rank on the periodic table. So hydrogen is the most abundant element in the universe, followed by helium and so on. And so one of the other phenomena we believe about nature is that, nature prefers simplicity, and life as we know it on Earth was built with sort of basic building blocks: carbon, nitrogen, hydrogen, oxygen, etc. And so while we don't know, and while it is certainly possible that life could exist on sort of non-carbon based, non-water based phenomena, we obviously have to be open to the possibility of trying to understand life as we don't know it. That is clear. But nevertheless, we think that the laws of physics are the same throughout our universe. It's fair to assume that the laws of biology may also be similar. Certainly the laws of chemistry are going to be the same wherever you are in our universe. And so we think that there's at least some merit to the notion that water is an important ingredient to at least a very diverse set of life on our own planet. So, and water is very abundant in space. I mean, we have observed water as a molecule in intergalactic space, so great distances, meaning also a long time ago. So there's, evidence of water forming in space from far away and long ago. So water is a very common phenomena. And so again, a question that we don't know the answer to, and you mentioned, life, definitions of life. One thing that's very interesting to note is there is no really good universally agreed definition for what life is. We know a lot about what life does, but we don't know really what it is. So anyway, we do have to be open to other possibilities, but there's a lot of evidence to suggest that looking for life is, we know it at least has some sound basis in science.
We have so many questions, very interesting ones. Jim Fitchbine asks, if we did receive a signal that we believed came from some sort of intelligent source, if we did receive such a signal from afar, what would we do? And let me add to that by making the obvious point that if we did, of course, it probably would have come from a source perhaps thousands or millions of years ago. So if you suddenly got such a signal and said, oh my goodness, this has got to be from an intelligence source, what would you do with it?
Yeah. Well, of course, that's a question we get all the time, and it's a great question. First and foremost, the first thing we would do is, if we detected with our instruments or any of our telescopes a signal that we could verify was, not from a local source, we have to deal with radio noise in a very radio noisy planet, and make sure that anything we observe is truly coming from far away. So step one is actually to verify the signal in discovery. So step one would involve contacting other radio observatories, assuming this was in the radio domain as a discovery, and get them to verify that, yes, the location of this signal is far, far away. And indeed, the signal itself would probably be relatively straightforward to understand as being technological in nature, as opposed to something of a natural process. But you raise a good point in terms of the distances and the scales. I think people often confuse the SETI endeavor as a hope for communication. I mean, that would be lovely. And if in fact there were technological civilizations within, 5, 10 or so light years, one could even conceive in one's own lifetime of a conversation where there's back and forth information being exchanged taking place. But statistically, the likelihood of the possibility of technological life is such that, as you mentioned, Arnold, it could be thousands or hundreds of thousands of light years away, in which case, certainly the possibility of a conversation, if you will, is not possible. But of course, the importance is simply what it means for humanity. And I think one of the things we believe about the SETI endeavor is that it's a hopeful endeavor. Any signal that we find, it's likely, again, statistically, going to come from a civilization far more advanced than we are. The Earth is 4.2 billion years old. The universe is 14.2 billion years old. Humanity's been around on this planet for a few 100,000 years. Technology's only been here for 100 years. If you think of the onset of technology as being that point in time when we started using the electromagnetic spectrum to do things like broadcast radio signals, et cetera. So we're 100 years into our own planet's visibility from far away. Our signals haven't extended beyond 100 light years from Earth, and they're very, very weak at that point. But so if we were to discover something, it would be just statistically likely that this is a civilization far more advanced than we are. And that means that, if they had a similar evolutionary process as we did and faced some of the same challenges we do today as a civilization, some of which are self-induced, but they survived all of that, maybe that's a good sign. That's a hopeful sign for the fate of humankind.
Reflecting on current events, Gerald Gibeon asks, could you elaborate on how you worked with NASA on the Perseverance program? Let me just make a personal comment. When I first saw the pictures that were taken from Perseverance of the landscape on Mars, I was hoping I would see little creatures walking back and forth.
Weren't we all?
Anyway, so what did you do with NASA on that program?
So it's more about what we are doing or will do than what we were doing. We have a couple of places we were involved. So one of the interesting areas that we have a contract for with NASA is a field called planetary protection. Planetary protection is about preventing forward contamination of other worlds we might visit, or backward contamination, bringing things back. And of course, the Perseverance mission does include caching samples that we hope within a 10-year horizon, we have the opportunity to go and retrieve and bring back for analysis. So we hold the contract with NASA for planetary protection, which involves, for example, going to spacecraft in their clean room, in their assembly stages, and making sure that they are as free and clear and sterile from human or Earth-based biology as possible before they visit another world. So we don't want to go to another world to look for life and find ourselves. So making sure that spacecraft are sterile and clean, which is technically completely impossible, but as clean as they can be, is very important. And our scientists and engineers do the work to do the so-called biological assays that make that analysis. As far as the mission itself is concerned, one of the instruments on board, in fact, the key instrument for the mission is something called a Raman spectrometer. And we're part of the Raman spectroscopy team. So one of our scientists who's an instrument developer and Raman spectroscopist is part of the team that is using the Raman spectrometer to look for signs of biology. So it can detect biological organisms and the building blocks for life, as well as mineralogy and so forth, so we can understand composition of soil and soil samples, regolith, and things of that nature. So we're primarily involved in the life detection side of that mission, and up front, we were involved in the planetary protection side.
I have a few questions that relate to science. Richard Bartholomew wants to know, is there anything faster than the speed of light?
Not clear. There's been signs of possible faster than light phenomena observed at CERN, at the particle accelerator on the France-Swiss border. And frankly, I haven't kept up with those observations enough to know if they've been verified, sustained. I mean, these phenomena, if observed, have been infinitesimally short in time, and so on. But that's not to say that faster than light speed travel isn't possible, or maybe some interesting things like the ability to fold space and time. If we think of the fabric of space and time as something physical that could be manipulated. So I think it's fair to say that, there are technologies and capabilities, yet to be discovered that are well beyond our comprehension today. I mean, if you think about where our technology is now, which would have been incomprehensible to our ancestors only 150 years ago. Imagine where we'll be in 150 years from now, or 1,000 years if we make it that far, or 10,000 years. So I don't know, but the laws of physics are interesting. They seem pretty fixed, but we do bend the rules from time to time. And the only other thing, though, is even if we were to develop the capability as a species to either ourselves as biological passengers, or on a hardware-based basis, like just sending a probe, to travel faster than the speed of light, it still doesn't help you much when you're talking about thousands of light years separating phenomena. The space is just huge. So the Star Trek warp speed, it really doesn't help very much when you talk about the scale of the actual universe.
Richard Bartholomew is really curious today. He wants to know if there are different seasons on Mars. And I would extend that to ask, from all we know, would most of the exoplanets that we know about, would they also experience seasons in the same way that the Earth does?
Yeah. So the reason that the Earth has seasons is because as the Earth goes around the sun, the orientation of the Earth between its north and south poles is not vertical. If it were perfectly vertical and the Earth went around the sun in this way, there would not be seasons. Every latitude would have the same weather year round. But the fact that the Earth is tilted slightly on its axis, it means that in our summertime, as the Earth spins, we get a longer bit of exposure on the northern hemisphere to the sun than when we're on the other side of the sun. And now it's the southern hemisphere that gets that longer exposure as the Earth spins. So that's why we have winter and summer, spring and fall, is because of the tilt of the Earth's axis as it revolves around the sun or orbits the sun. Mars does have seasons. Mars' axis is also slightly tilted, and it has seasons. And we observe, I mentioned earlier the observation that was announced just a few years back that of so-called flowing water on Mars, particularly on the walls of the canyons created, or the vertical surfaces created by meteorite or meteor impact sites. And these are seasonal phenomena. So we see them coming in the summer when things warm up a little bit and then going away. So Mars has seasons. The most common star in the universe, as far as we know, certainly in our galaxy, is a type of star called an M dwarf. M dwarf stars are much older than the sun, or can be. They tend to be cooler and smaller, and they have planetary systems. A very interesting planetary system called TRAPPIST-1 has 7 planets around it, all about the size of Earth, and at least 3 of them are in the habitable zone of that star. And they're in a very tight-in orbit, much closer than Earth is to the sun. But we understand those planets are tidally locked, just the way the moon is tidally locked to Earth. So we always see the same face of the moon. In those systems, the planets always have the same face to the sun. Even there, however, scientists have evaluated the possibility of, well, what does a weather system, what does an atmospheric system on a tidally locked planet look like? And there have been calculations that a planet that is otherwise in the habitable zone, on the one hand, it would be getting baked on one side and be frozen on the other side. However, at the perimeter of that side facing its sun, you could well have the conditions to support and sustain life. So in general, seasons are going to be based on whether a planet's axis has a slight tilt, and certainly evidence in our own solar system suggests that's a fairly common phenomena. Some planets around older, smaller stars are going to be tidally locked. But it is amazing the variety of planets we've observed. I mean, planets the size of Jupiter whipping around their sun in 4 days. So, I mean, there are things that we've discovered that we couldn't have even imagined. And I'm sure there's many more discoveries like that yet to be made.
One of the stories that never seems to go away, and it seems to be surrounded by conspiracy theories, is Roswell, New Mexico. Mm-hmm. Keeps coming back into the press. And Jerry Schwendeman asked the question that we think of it as the alien capital of the United States, but do you think the SETI...
Oh, that was Washington.
Yeah. Well, good point. Jerry wants to know whether SETI believes that there is any objective evidence to support any extra planetary origin for some of the findings at Roswell.
Well, the short answer to that question is no, we don't. And a simple thought experiment is often worth deploying for a question like that. I mean, as I mentioned before, if we just talked about the closest neighbor where there could possibly be a planet and technological beings, that's Alpha Centauri. And even traveling at the speed of light, if you took into account the acceleration up to that speed and the deceleration that would be required to get to Earth, you're talking hundreds of years or more just to get from there to here. As I mentioned in my talk, if we took the New Horizons spacecraft, which is the fastest spacecraft we've built, at least going in a trajectory other than an orbit, it would take 17,000 years just to get there. And we certainly don't have the technology to send biology over such a distance. And not even hardware over such a distance, at least not in any time frame that is meaningful. So even at light speed, the opportunity to send biological species or life forms is very limited and very, very challenging. There's also issues of the impact of microgravity and exposure to radiation in interstellar space that is very hard for biology as we understand it. So, the notions of sending craft from such great distances is hard for us to fathom. However, so let's take the thought experiment now and say, well, okay, but we're very infant in our technology. Surely there are civilizations out there who have vastly more superior technology and maybe have the opportunity to travel these great distances. Fair enough. Do you think if there's a technological species out there that has solved those problems in such a way that they could send hardware or even biology from some tremendous distance to Earth, that they would crash on our planet? I mean, really? This kind of defies logic. We have cars that can drive themselves. I think it's hard to imagine some civilization having the technology to get here with hardware or biologyware and crash into our desert. And also, if there were small spacecraft that were exploring our environment, coming from far, far away, they certainly didn't come those great distances as little planes, with a single occupant. There'd be a mothership. There's no sign of a mothership. Something as large as required to potentially hold multi-generational beings and support little craft going for exploration would be massive and very difficult to hide. So I don't know, we take with a grain of salt these observations. Now, that's not to say that UFO are not a real phenomena. They're called UFO because they are unidentified flying objects. They're flying around. They're doing things that we think, in terms of our own understanding of aerodynamics and mechanics, are difficult to explain or describe, and therefore they're unknown. So we don't know what they are. But the idea, from my perspective and ours, that these are craft that have come from a great distance to investigate our planet, seems unlikely. And but of course it's a fun question and one we get all the time.
If you're familiar with the ALMA project in Atacama, Hector Arzeno asks if you had any programs in collaboration with it.
Well, yeah. So we there is a program called GPI, the Gemini Planetary Imager, and one of the telescopes is at ALMA, and the other is in Hawaii. It's called Gemini because these are two twin telescopes. They're 8-meter diameter optical telescopes. There's, of course, ALMA is also a radio telescope observatory, but the Chilean Optical Observatory, where GPI is, our scientists are part of the GPI team, and that team has actually used ground-based telescopes to actually take an image of a planet around another sun. All the work that I mentioned on radial velocity, the Kepler mission, all of those are observations of phenomena that are a result of the presence of planets. They're not a direct observation of those planets themselves. But the GPI project was one in which the telescope was modified to include an object that would actually block out the star that was being imaged, just the way you hold your hand up, to block the sun. If you're trying to look at an airplane or something, in the sky close to the sun, you hold your hand up to block the light of the sun, and suddenly you can see things a lot closer to it. The same way, so the GPI telescope blocks the light of the star, and using a technology called adaptive optics, which compensates for the shimmer and distortion of the Earth's atmosphere, we've been able to actually take a picture of planets around another star, and in fact take enough pictures that we can actually see the orbital dance of these planets around the stars. So that's what our scientists have done with colleagues on the Chile observatories. But of course, another thing that we do in Chile is a lot of field work. So in fact, a lot of the work that goes on to inform missions like Perseverance and Curiosity, which start with, what are the tools and technologies we need to dig, to drill, to analyze material, to look for signs of life. First, where do we look? What's an interesting place to go? And then how do we look? And a lot of those technologies are developed by going into the field, to going places like the Atacama Desert, which has a lot of similarities to Mars, interestingly enough, and developing these techniques. So we have teams that every year go to the Atacama Desert and other places to do this technology development. So we're good friends with Chile and the Atacama and that part of the world.
The last question, I guess, is a philosophical one. Arthur Clarke made a statement: two possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying. John Blankley wants to know, what do you think he really means by that? And do you agree with it?
Well, I think what he means by that is, it's terrifying to think that we are alone. That really means that we are, our destiny is strictly and solely in our own hands, and that the challenges we face as a species existing on our own planet, which is an island with finite resources, which can't be continued to be populated by human beings, in an ever increasing population, and hope for its survival. So we have challenges, if we are alone, are pretty terrifying. I think what he meant otherwise was that, if there are other civilizations out there, and they discover us, they might not be so friendly, or they might be friendly, just as the Europeans who came to the North American continent and the South American continent didn't necessarily have evil intentions, but things didn't go well for the native populations in either place. So part of that, I think, comes from what we call an anthropocentric perspective on this question. In other words, we can only look at things and ask these philosophical questions from the perspective of human beings. And of course, that perspective includes a lot of knowledge about our failings and our misbehaviors and so on. So we're not the best example, perhaps, of what intelligent life may ultimately derive. My personal feeling is that because the challenges that we face right now with population, with pollution, with resource utilization, et cetera, with climate change, these are all serious and potentially existential problems that we have to deal with. So my feeling is, if a civilization has gone through that arc of near disaster, shall we say, and come out the other end and survived, then my feeling is that civilization has done so on the basis of some level of benevolence, some level of intelligence and benevolence that suggests, it's not necessarily going to be a society that then goes and, eats people on other planets. So my take is that, intelligent technological civilizations that have survived the challenges we now face are probably, better than we are.
Bill, thank you so very much. I want to apologize to several of our viewers whose questions we didn't have time to answer. We've gone beyond our usual time for good reason. You've provided us with considerable education and outreach, for which we thank you very much. So remember, everyone, tune in next week for another talk, and give Bill a big round of applause, even though we won't be able to hear it. So thanks again, Bill. Be in touch.
Welcome. And Arnold, if you like, since you have my contact information, any real fun questions, send them my way. We'll be happy to give them a shot. And I apologize for what are sometimes too long answers.
That's okay. Thank you.
All right. Thanks, everybody. Take care.